Welcome to Brain Vision.
In this question, we have this wave that has a peak-to-peak amplitude of 1 centimeter. It has a frequency of 100 per second. It has linear mass density of 120 grams per meter, and then finally tension of 90 Newton. Part A asks us to find the maximum transverse speed of a point. So we already did this equation in chapter 15, and the equation is ym times omega. But I think it will be more due to part B to actually quickly write out the derivation again. It's because we have this which is described by ym sine kx minus omega t. So when we want to find u is the derivative of y with respect to t. So ym negative omega cosine kx minus omega t. So the maximum value will be ym times omega, y equals -1. Okay, in this case, we have peak to 1 centimeter. So the amplitude is half of that, is 5 millimeter. We also what omega is. Omega is 2 pi times frequency, which is 120 hertz. So this gives us a maximum transfer of 3.7 meter per second, more like 3.8. Second, we want to find the largest transverse component of tension. What does that mean? So we have tension, and tension is always along the string. So, but then there is this horizontal component of tension. We find the maximal horizontal component of this tension. How do we find that? So this can be found if we, let's draw a zoomed out graph. So for a single component, the y, there is an x, and this angle, theta, this angle theta can be described by, actually, let's use a different angle. We can use this angle theta can be described by tangent theta equals delta y over delta x. But then, how is tension related to this theta? So tension is this tension has a transverse component. This is a transverse this is a transverse component and section of the tension. So the component of tension in this will be tension in the transverse direction was total tension times sine theta. So we need to use dy dx, like we will take the derivative of this equation this time with respect to find what tangent theta is, and then we will use that tangent theta, and we will take the maximum value of that. We will take the maximum value of theta to find what tangent transverse is. So the tau of transverse is. Okay, so let's first take this derivative. If we take this back to x, we get k times ym times kx minus omega t. So the maximum we could possibly obtain is k times tangent theta, which is also theta minus tangent is monotonously increased. Theta equals inverse tangent of k times m. So we need to find k first, then we can find theta. What is k? Is 2 pi over lambda, but we also do not know what lambda is. So we can say k equals 2 pi over lambda, but then lambda equals b over f. So because of that, k equals omega over v, and that's probably the easiest expression we can use for now. Okay, so omega is 2 pi f, v is square root of tau over mu, and then tau over mu is this whole thing again times ym. So that is inverse tangent of 2 pi times 120 hertz over square root of 90 Newton over 0.12 kilogram per meter times ym is 5 millimeter. Our calculator tells this is 7.8 theta. So that is a mass theta we have. And the larger the theta is, the transverse component of the tension is. So the largest transverse component of tension happens when it equals 7.8, and that is 90 Newton times sine 7.83 degree, and it is 3 Newton. So we see that here it's actually sine and theta was actually pretty because theta is very small. So like sine theta and tangent theta, they don't differ that much. Okay, now we can do part C. What does part C say? Part C says we have to show that the two maximum values calculated above, they will occur at the same phase value for the wave. And then we ask, what is the transverse displacement of y of the string at these phases? So that is asking us to find this place. Well, it's easy to say why they occur at the same phase. Both of them, if we look at this, both of them are derivative of this wave equation, one with respect to t and one with respect to x, and both of them get their maximum when cos x minus omega t to a maximum. So that is the explanation for part C. It is if we add 5 over here, we will add a 5 over here. Conclusion is still the same. It's a phase whatever that maximizes cosine kx minus omega t plus 5. So that's the first part of C. The second part of C is that we want to find out the displacement of the y at that point. That is also not so hard because we have cosine kx minus omega t plus 5 equals plus or minus 1 at these points. cosine equals plus or minus 1, we know that sine kx minus omega t plus phi will be equal to 0. Y equals again this equation, ym times sine something equal to 0. So for part C, the transverse displacement y will be 0. Okay, now part D, what is the maximum energy transfer along the string? The maximum rate of energy transfer along the string, well, we can find what P is. That is P equals work. So that's like the rate of energy transfer. But then the amount of work similar, we can work equals 1/2 of mv squared, but it's easier since we already find that the transverse tension is equal to tau transverse. So this is equal to transverse times, because force times is the work you do, and then over delta t. So delta t is u. This is tau transverse times u, and obtain a maximum when both tau and u gets a maximum, which we know will occur at the same time. So this is equal to 12.3 Newton times 3.8 meter per second equals 46 watt. So since I'm running a little bit out of space, I'll get you a new page. Let me just make sure I have all that here. Part B. Part C. Part D. That's A. And now I will start a new page to do the rest of the question. Okay, now it's time to look at part E. For part E, we say what is the transverse displacement y when this maximum transfer occurs? Well, that is just 0 meter, because that's the maximum occurs when both the and the transverse gets to the maximum, and when that happens, the displacement is 0. So here, when the maximum power is obtained, displacement is also 0. Part F. Part F asks, what is the minimum rate of energy transfer along the string? Okay, again, we can go back to the past equation. We already know what it is. It is probably 0, because P is, again, it's U times tension, and both the transverse tension, they have a cosine, kx plus or minus omega t plus phi. They have a cosine side. So previously, when we were looking for the minimum value, we set all of these cosines to 1. Well, for the minimum value, well, we'll just set them to be 0, and then the total power will be 0. And you can also just visualize it. Wave is here, there's transverse component at all. Everything's like horizontal, so we don't have any work going on. F, G. Another way of thinking about that, at these points, like at the maximum points, the instantaneous speed is 0, so we don't have any kinetic energy. So because we have no energy, in this case, like there is no energy and there is no power. So again, the power would be 0 at all of these peak points. Finally, is part G. And for part G, we ask, well, what is the transverse displacement y when these minimum value happen? Well, when cosine equal to 0, sine kx minus omega t plus phi will be equal to maximum. So if we choose this equation, it will be the maximum possible when it happens. And it could actually be both positive or negative. So it could have negative value, which is positive negative 0.5 centimeter. Okay, so these two are the solution for this question. This is part A to D, E to G.